Hey guys, welcome back. This is going to be the 4.6 instructional video, and we're going to break it into two parts. So we'll cover the first part today, then we'll cover the second part in another video. So to kick things off, what I want you to do is I want you to pause the video, and I want you to think about, in a deck of cards, what is the probability of drawing this card? This card being the 9 of spades. What's the chance you have a deck of cards, you draw a 9 of spades? Well, what you probably are thinking about is, okay, I learned in 4.5 what theoretical and experimental probability is, and I'm not physically drawing the card, so this is a case of theoretical. What do we do for theoretical probability? Well, we think of the number of all possible outcomes, because this is a case where all the outcomes are equally likely, right? Your chance of drawing a 9 of spades is no more likely. It's not as if that card is somehow thicker or bigger or weighs more than the other cards. All the cards are equally likely. So you look at all the potential cards you could draw and how many of them there are. Well, that number would be 52. If you're not familiar with playing cards, there are 52 cards in a deck. 26 red, 26 black, 13 in each suit. So 13 diamonds, 13 hearts, 13 spades, 13 clubs. There's 4 of each number and 4 of each face card. And then there is one specific card that meets all the criteria. So there is one 9 of spades, if you will. Okay? So kind of gives it away, but depending on what you wrote down, hopefully you came up with 1 out of 52. Again, the logic being we're calculating theoretical probability. So we're going to, in our denominator, have all the possible outcomes because they're equally likely when we're looking at drawing cards. It would change if they weren't equally likely. So we're taking all the possible outcomes. And in our numerator, we're going to have how many we're specifically interested in. I'm not interested in the other 51 cards. I'm interested in drawing the 9 of spades, which there are 1 of. Again, shouldn't be super new. Pretty much review from 4.5. But let's start thinking about this next question. What is the probability of me drawing a 9 of spades and then drawing a 2 of hearts? So I have my deck, draw the 9 of spades, then draw the 2 of hearts. That whole event together, what's the chance of that occurring? Well, let's think. Well, first things first, we have to make a little distinction because there's 2 ways I could do this. You see, I could have my deck of cards and go, okay, I'm going to try and draw the 9 of spades, draw it, and go, sweet. But then I have a choice. I could either put it down and have the rest of the deck and go, okay, I'm going to try and draw that 2 of hearts. Or I could take that 9 of spades I drew and put it back in the deck, reshuffle, then try and draw the 2 of hearts. It's going to affect how we think about the problem. So let's think about it. First things first, if I replace the first before drawing the second, okay? You might be sitting here going, whoa, I have never thought about probability in a manner like this. This is totally new. I'm not sure I'm really getting it. Well, before we answer this question, let's maybe answer a simpler one. What is the probability? What is the probability? When you see the P in the parentheses, it means probability. What's the probability if we're flipping a coin of you flipping a coin and getting a heads? What's the chance you flip a coin and get a heads? Well, it's probably a no-brainer. You probably sit there for a second and go, okay, 50% or 1 out of 2. And again, what you're doing there is there are 2 potential equally likely outcomes, heads or tails, and you are interested in one of them, that being the heads. Well, let me ask you this. What's the probability that you flip a coin twice and you get heads both times? Or the probability of getting a heads and then another heads? Well, this one's a little bit more tricky. But let's think about it. Our gut probably says, well, the probabilities don't change when I flip a coin, right? You flip a coin, one flip doesn't affect the second. So it might be tempting to think, oh, it's still 1/2. 1/2 chance you get a heads the first time, 1/2 you get the second time. So 1/2. And that's tempting, but it doesn't really get the full picture. To get a better idea, my question, to go off the question, would be, let's think about it. What are the different outcomes I could get if I flip a coin twice in general? Well, you're probably sitting there going, well, you could get a heads the first time and a tails the second. This is actually probably one we would expect, right? Heads and heads doesn't really match our theoretical of there being a 50%. That would be unlikely, right? In an ideal world with a 50% chance of a coin getting heads or tails, if we flip it twice, one would be heads, one would be tails. Okay? But another option, maybe this is a better way to write it, heads and then a tails. But then if you think about it, you go, well, the reverse could also occur. Right? Maybe the first flip you get tails, and then the first or second flip you get heads. And then the more we think about it, we go, well, probably not as likely. I could theoretically get a tails and a tails, right? I flip a coin, tails, flip a coin, another tails. And the same would be true for heads. What we've done here is we've created our sample space. We've listed all the possible outcomes of flipping a coin twice. Each time you flip a coin, you have 2 options. We've listed, if we flip it twice, then we're going to have 4 options. We've listed all of them here. So when we think about probability is always some sort of part over whole. What is the part we're interested versus all the options? Well, here, and this is the first way we can dissuade the answer of 1/2, we have 4 different options in our sample space. There are 4 potential outcomes when I flip a coin twice. How many are we specifically interested in? Well, our question is heads and heads, and there's only 1 out of 4 ways of flipping a coin twice and getting heads and heads. Thus, the probability of flipping a coin, getting heads, flipping a coin, getting heads again is 1 out of 4, or 25%. Now you go, okay, great, Mr. Carter, let's think about the card problem. Well, we can think about it that way, but instead of dealing with just 2 events with 2 outcomes, think about what we'd have to think through. We'd sit there and we'd go, okay, there are 52 different cards, and no matter what card I select the first time, there is 52 different options. So what do I mean by that? Well, let's say I select the ace of spades. If I put that card then back in the deck and shuffle them up, how many different options are there for the second choice if the first is ace of spades? Well, there's 52. Well, what if my first card was a jack of diamonds? How many are there for that second selection? Well, again, 52. Well, what about the 9 of spades? That second selection, if I draw the 9 of spades, I put it back in the deck of cards. How many options are there for that second choice? 52. You can see how complex this is going to get. But let's think about this a little bit different, and then we'll come back to the cards. What is the probability of getting 1 head? The first flip, what's the chance you get heads? Well, there's a 1 in 2 chance. We answered that question above. Now just analyze the second flip. What's the chance of getting a heads? Well, again, it's 1/2. If we multiply those 2 together, what do we end up with? 1/4, which is the same thing we got when we thought about it and wrote out the entire sample space and identified how many we're interested in. The quicker way of solving and probabilities is to multiply the probability of each individual event occurring. What I do here is I take the probability of selecting heads times the probability of selecting a heads, and I get the probability of flipping the coin twice and getting a heads and a heads. Now, how does this apply to our card problem? Well, let's go back. You see, the sample space is going to be somewhat nasty to write out for all this. Because think of all the different options. For every single potential card you select first, there are 52 options. Well, 52 cards, each having 52 options, that's going to lead to a ton of options. But think, we have an and probability occurring here. So we can just multiply the probability of each event occurring, and we'll quickly arrive at our answer. Think about the 9 of spades. What's the probability of drawing a 9 of spades? Well, it's 1 out of 52. 52 cards in the deck, only one meets the identification of 9 of spades, and so the chance of drawing a 9 of spades would be 1 in 52. Similarly, for the 2 of hearts, there is again a 1 in 52 chance you select that card. Now, this probability could change if I just said a 2 in general, but again, we're working specifically with the 2 of hearts. There's only one of those in a deck of cards. So I know the probability of drawing a 9 of spades, and I know the probability of drawing a 2 of hearts. So how do I answer the question, what's the probability of drawing a 9 of spades, putting the card back in the deck, shuffling, and then drawing a 2 of hearts? Well, I can figure it out by multiplying them together. When I multiply 52 and 52, I get 2,704. 1 times 1, I get 1. In other words, if I have a deck of cards randomly shuffled, there's a 1 in 52 chance that I will select the 9 of spades. What is the probability of me selecting that 9 of spades, though? Putting it back in the deck, shuffling, and then getting the 2 of hearts? It's only a 1 in 2,704 chance. Now, where could we think about this if it's still a little confusing, the multiplication, thinking about the sample space? Well, again, this is what I was alluding to earlier. There are 52 different options for your first card selection. But no matter what card you select first, that card is then going to have 52 different options for the second selection. Well, if we have 52 options for our second card, 52 different times, what that leads us to is a total of 2,704 potential combinations for cards. In other words, there's 2,704 different ways to select a card, put it back, and select a different card. Now, why is 1 our numerator? Well, 2,704 is the amount of our sample space, the number of potential options that are equally likely. But we only have 1 in the numerator because there's only one way of selecting a 9 of spades, putting the card back, shuffling, and selecting a 2 of hearts. Again, this is not the case if we were just working with 9s and 2s in general. So hopefully you get the idea here. When we're thinking about compound probability, what about this and this occurring? The simplest way to solve your problem is by multiplying. Now let's think about the second question. Here we answered, what's the probability of drawing a 9 of spades and replacing, aka I draw the 9 of spades, put it back in the deck, and then draw the 2 of hearts? What about if you don't replace the card? What are the odds of me drawing a 9 of spades, getting it, setting it on my desk, and then drawing a 2 of hearts? Well, again, the first action that's occurring is drawing the 9 of spades, which we good and well know by now has a 1 in 52 chance of occurring. The question becomes, what are the odds of drawing the 2 of hearts, but now I've set that 9 of spades on my desk? Well, it's an and probability. I know I'm going to multiply. But what we have to account for is that card is now on my desk. Now, does that change how many cards we're interested in? No, there's still only 1 2 of hearts left in that deck of cards. But what will change is the denominator. Why will the denominator change? Well, because if I draw that 9 of spades and set it on my desk, there are only 51 cards left. So not replacing the card is going to produce a different probability for me than if I do replace it. I solve this by multiplication, and I find that there's a 1 in 2,652 chance. Let me triple check that math there. that I would draw a 9 of spades, get it, set it on my desk, and then draw the 2 of hearts. Now, if we turn these into percentages, we find that this is our decimal. And again, they're super similar. So if we turn these into percentages, well, what you can see is while they're very similar, the second one is slightly higher. Second one is slightly higher. And this should make sense to us, right? If I get lucky enough and I draw that 9 of spades, which happens in both cases, which situation has the better odds? Well, the better odds would be if I set that 9 of spades back down. Because if I put that 9 of spades back in the deck, well, then there's a chance I could draw it again, making it less likely that I get that 2 of hearts I'm after. So hopefully this makes sense. Again, what you should be walking away with right now is when we work with compound inequalities, specifically and situations, where I want to see what's the chance of this happening and this happening, we are going to use multiplication. Okay? Now let's get into some definitions. Okay, we've gone through an example. Let's think about some definitions. The 2 definitions that I want you to think about are dependent and independent events. What is a dependent event? A dependent event is when one event is influencing something else. One event influences something else. A great example of this is if I don't replace the first card. Okay? If I set that card on my desk, that affects the probability of what the second card is going to be. It is dependent. If you want to think of an example for that, let's say I'm trying to find the probability of drawing a 4 and drawing a 5. And let's say I'm also trying to find the probability of drawing a 5 and drawing a 5. Well, if we think about these, and I'll write my answers down here below. What's the probability of drawing a 4 out of a deck of cards? 4 out of 52. What's the probability of drawing a 5? Again, not replacing. So if I draw that 4, I set it on the desk. Well, if I set that 4 on the desk, there's a 4 in 51 chance. Meaning there's a 16 out of 2,652 chance that I would draw any 4, set it on my desk, and then draw a 5. Now, what about the other situation, drawing a 5 and drawing a 5? Well, again, 4 out of 52 chance I draw a 5 out of a deck of cards. If I do, set it on my desk. But then there's only a 3 in 51 chance of drawing another 5. Why? Well, because there are only 4 5s in a deck of cards. And if I just drew one of those 5s and I set it down, now there are only 3 left. Why do I illustrate this point? This is known as not replacing the card as a dependent event, because the chance for this second one, the odds of your second event, while it's the same exact event, drawing a 5 being the second event, the probability of that event occurring depends on what happens beforehand. If I draw a 5, set it down, and then try and draw a 5, my chances are less than if I drew another number beforehand. This is dependent probability. When events influence one another, the occurrence of one event affects the probability of a second event. You want to think of a real-world example? Dependent probability would be sports and weather. Weather, those two things are considered dependent events. The quality of sports being played in a rainstorm is probably worse than that of those played on a nice day. The quality of the sport event depends on the weather, okay? Dependent events. The opposite is independent events. This is where events do not influence one another. This is the situation of me putting the card back in the deck. If I draw a card, no matter what card it is, if I put it back in shuffle, my second selection is not impacted by my first whatsoever. Okay, why? Because I still have a full deck of cards and they're all shuffled. Those are independent events. In that case, it doesn't matter what you drew first. It's not going to affect what you draw next. Okay, good examples of this: rolling a die. Whatever you roll does not influence what you're about to roll. You don't somehow roll a 6 and become more likely to roll a 2 on the next time. It's not the case. Same with flipping a coin. Just because I got heads last time I flipped the coin doesn't mean I'm somehow more likely to get a tails on the next flip. Independent events. Dependent, the actions of a first event affect the second. Independent, it doesn't matter what happened beforehand. The probability stays consistent. Okay, so that's going to wrap it up for this first part of 4.6. Again, we will dig into this more in the next part, but hopefully the card example makes some sense and it's a good introduction. As always, let me know what questions you have.